To get started, so off we go. Real quick before we get into the math, I sent an announcement about this, but I just want to make sure everybody saw. I don't know what took me so long to figure this out. This is perfectly obvious in retrospect. I have now made a copy of the content syllabus where I just rearranged the rows to represent the order that we're actually covering the material. It took me 10 seconds. I don't know why I didn't think of it before. Anyway, here it is. I encourage you to look only at this copy of the content syllabus. It is, I believe, unless I did something dumb, identical to what we have on the course website, right? But again, just written in the more convenient order. So you'll notice it starts with 1.6, as we did, right? And you'll notice now, and we're going to get to this today, 3.1 is squeezed in between 2.4 and 2.5. That's one of the things we're going to do today. Anyway, I would encourage you to just use this. This is perfectly consistent with the way my notes are ordered and with, again, what we're going to be doing in lectures. And therefore, by the way, with the order that we're going to be making homework exercises assigned. So I would encourage you to just look at this instead of the course version. Okay, did I see a hand? Yeah.
I was just going to say another suggestion too. You could put them in the same file and just have them as a sheet.
Yeah, I thought about that. The problem there would be that the students in the other section would wonder what on earth is going on with this other sheet, and they just I think it would create.
Not on the same.
They're doing whatever their instructor wants to do. But I appreciate suggestions. Yeah, absolutely. Okay, all right, so back into math. Here's about where we left off last time. Let's talk about higher order partials. Y'all remember higher order derivatives from single variable calculus, right? If you have a function, you take its derivative, it's another function. You could take its derivative, right? So the same thing happens with partial derivatives. If you have a function of several variables, the partial derivative is also a function of those same several variables. So you can take its partials too. And here's some examples. So, whoops. That's good to know. Here's a function. X partial, Y partial. Results in notations. That's all old news. I'm sure y'all have mastered all of that. But now let's look at this X partial. The X partial is itself a function of X and Y. So I can talk about its X partial and its Y partial. And you can compute those. The notations are a little bit worthy of comment here, just because there's a seeming backwardsness to this notation. So let's take this very carefully. Starting with the X partial, right? And you can see I've got the X partial as a sort of a starting point for these notations. Let's look at how I would represent taking the Y partial of that X partial. Here's how I would do it in the Leibniz notation. Partial with respect to Y has to be written on the left. That's the standard. And here's how I would do it in the Newton-like notation. It's a subscript, which is on the right. Again, it's a standard, but it's sort of the opposite side, right? Now, as a result of how those are written, we shorten those notations with these things over here. And what's awkward, and this is just the way it is, I mean, you kind of have to do this, right? The Y partial is on the left in the first notation. The X partial is on the right, but quite the opposite with the other one where the X is on the left and the Y is on the right. So if you, I mean, again, what else are you going to do? Right? Green, blue, green, blue. Blue, green. You kind of have to do that, right? But that leads then to this uncomfortable seeming contradiction in the notation that, hey, how come the Y is on the left over here but on the right over there? These are the same thing. Well, it's because our hand is forced based on our earlier choices about how to write these partial derivatives. Yeah.
And if we were supposed to, if you were told to get the partial like like y derivative of this, would it just be also on towards the left as well?
Well, the y partial in Leibniz notation would be on the left, but the subscript in which you indicate your next y partial here would be on the right. So you just continue this pattern.
Can you just use one notation?
Can you just use what?
One notation, or you have to do both?
You have to be aware of both, because both are out there and are in your future whether we like it or not. Yeah. So this is not a you get to pick one situation. And by the way, there are some situations where it's really almost essential that you use this notation. Mm-hmm. And there are some situations where it is really almost essential that you use this notation. So yeah, there's kind of no way around it. Yeah.
Did you see the observation at the top?
Oh yeah.
Okay.
Yeah. So remember, these notes, by the way, are available on for download, and you can at your leisure. They're on the website. Okay. So heads up about that notation. It's unfortunate, but again, what are you going to do? Okay. So here's a coincidence. So it would seem, anyway. Look at that. Those are the same. How about that? What are the odds? Well, it turns out pretty good. So for a large category of functions, this always works. For a very large category, yes.
So in this case, we only have two variables, right?
Yes.
What would happen if you had three?
Same, exactly what you would think. It's totally analogous.
And so would C be also on the left if it's on the left?
Whichever one is first. It's not a question of how many variables there are. It's a question of which partial acts first, which one is second, which one is third, and you go in the orders that we've set the precedent for right there.
Also, the first one is on the right, and then the second one, and then the third one on the left.
Depending on which notation, yeah. Right, yes.
So the notation doesn't matter between the two. If we were asked a question on it.
Well, sadly, it really does matter because I hear what you're saying. You will get the same result for a large category of functions, but two things. First of all, not all functions, just a large category, right? And second of all, depending on what you're doing, you may or may not have demonstrated that the functions that you're looking at are in that appropriate category. And so you can't assume, you can't just be sloppy with it. You do have to be careful with it, even though it won't affect your result. But as I've said a million times, the result isn't what matters, it's the reason. Is that satisfactory? Yeah. Okay. All right. So this nice coincidence happens very often. In order to be able to state this precisely, I need to talk about this term, this notation, CK. This is a particular category of functions, and specifically, the K says what order of partials are we going to talk about, and the C says I need those to be continuous. And by the way, they have to exist, but that's implicit. If they're continuous, of course they exist. Right? So the C stands for continuous, and the K stands for how many partials have to be continuous. Okay, so the theorem then is that if a function is CK, and I'm going to kind of gloss the notation under the rug here because it's just notation. It doesn't matter what order you take your partials, and all the rest of interpreting exactly what this is just fancy talk. Notice that the subscripts I1 through IK, J1 through JK are all of the same actual subscripts. So these are all the same partials, just rearranged. In other words, I'm taking these partials in different order. Okay. So again, short version, if your function is CK, it doesn't matter what order you take the partials. You'll always get the same thing. Yes?
Sorry, could you please repeat what CK is?
Okay. So CK means how many partials are we going to talk about?
Oh, okay.
And the C says they have to exist and be continuous.
Okay, so
Yeah. Okay. All right. So let's talk about what these mean geometrically. After all, this is just algebraic fun and games. If it doesn't mean anything natural, why would we ever do such a thing? Right? So what do these look like geometrically? I remind you, what things look like geometrically depends on what kind of picture you're looking at. So again, you have to have these partitions in your mind of how do I interpret calculus in one context, like graphs, like we're about to do here, versus what do, whatever construction you're interested in, what do they look like on, let's say, in the context of level sets, right? Totally different geometry, completely different constructions, completely different calculus. Make sure to keep these partitions in your mind. The graph context is where good things happen. Let's talk about, let's see here, let's do FYY first. What does FYY look like? So let's think about how we compute this. How do we compute FYY? Remember, step one, hold x constant. So I'm going to take f, I'm going to hold x constant, and then after that, I am going to continue to hold x constant. Right? So for the entire calculation that I do when I compute FYY, x is constant. And geometrically, I can represent that very conveniently as, well, yep, x is going to be that value for the whole calculation. So said differently, I'm going to be on this cross-section that I can draw very conveniently. Right, that curve for this particular Pringle. That curve is what I'm going to be looking at when I take the partial derivatives with respect to y. Or I guess I could say, I'm going to take the derivative. Because there is only one variable, that being y. Right? So what do derivatives look like? What do second derivatives look like for single variable functions? Well, they're concavity. Old news, right? Calc 1, way back. And so, in fact, I can see straight away this is clearly concave up, and being concave up, FYY is positive. Everybody see how that works? So now, analogously, and I'll go quicker through this, leave you all to fill in the blanks. If you're interested in fxx, you're going to be holding y constant, which means your cross-section is going to look like that. Again, for this particular graph, which looks kind of like a saddle or a Pringle, that cross-section in the x direction, where y is constant, clearly concave down, fxx is negative. Is that cool? Yeah. Okay, so I'm going to call this good news. I'm going to call this exactly what we would expect. Second partials tell you about concavity. Okay, you got to think about which direction the concavity goes. By the way, notice one of the really cool thing about this example. At this one point, there are two different concavities. It's concave up in one direction. It's concave down in the other direction. That's weird. There is no single variable analog to that. This is uncharted territory. Brand new idea. Only exists in multivariate calculus. Okay, yeah.
Are there second partial derivative gradients?
Not really. There are various different constructions that we'll get to some of those later in the course, and some of them we won't get to in this course. Not in the way that you're probably thinking about it. Not really, but there are some things that are kind of reminiscent of that, but we're not going to talk about that right now. Yeah. Yes.
Could you please show again the curve when we have if you take the derivative with respect to y?
Yeah, so if you're going in the y direction, then this is the cross section.
So you're keeping x constant?
Yes. Because that's how y partials work. Yeah, that's right.
So how do you, so this is x instead of x?
Okay, all right. So here's where it gets tricky. What if you want to do a mixed partial? Oh, yeah, okay, last question.
Will they always have the same point of inflection? Like on that graph you showed, it looked like the x and y codes had the same point of inflection.
I happen to have picked a point here that's like sort of the special point on this particular surface. That was just for artistic convenience. Okay. But yeah, no, in general it won't be the sort of the nice special point. Yeah. Okay, here's where things get weird. If you want to do a mixed second partial, here we're looking at the x partial of the y partial. I cannot make a single variable argument like I did previously, because neither variable is constant for the whole calculation here. It's just not, Right? Okay, so I'm going to have to take a completely different point of view on this. And by the way, the picture is very hard to draw. The picture is sufficiently hard to draw. This is what I came up with, and I'll explain the details over the next several minutes. But notice I didn't even draw the surface. I just drew some particular selected tangent lines to the surface. And again, I'll talk through those details in a minute. But I wanted to explain first why I did not draw the underlying surface. And the reason is because it makes the picture even more confusing to add an attempted, drawing of the underlying surface to this. It just doesn't help. So I spent some time playing with it, and I came to the conclusion that it is all downhill from here. So that's why this picture is what it is. Okay, so let's start, though, with trying to make sense out of this. Let's start with the very first thing we do to f, which is to take the y partial. We know what y partials look like. They are slopes of tangent lines in that direction. And so, for example, at this point here, there's the y direction. And now I can talk about what does the tangent line look in that direction. And I'm going to say I get something like this. Not that you can conclude that from this picture. I'm just, again, use your imagination. There is some surface for which this would be the tangent line in the y direction. So some line, let's say it's that. Now, look, I can do this same thing at various other points, right? At that point, there's the y direction, and maybe that's what the tangent line looks like there, etc. Various points, y direction, tangent line, y direction, tangent line, y direction, tangent line. You get these various different tangent lines, all in the y direction, but all at different points. I'll explain why I'm doing that in a couple seconds. So a bunch of different tangent lines at different points, but all in the y direction. Okay, next question. How do I interpret the x partial of the y partial? Now here's where a lot of students mess up. The first thought is, oh yeah, okay, x partial, that means slope in the x direction. Not here. Because the x partial means slope in the x direction on the graph of the thing you're looking at the x partial of. And we are not looking at a graph of the y partial of f. We're looking at a graph of f. We do not have a graph of the y partial of f. So I cannot interpret the x partials in terms of slopes. I just can't do it. So I'm going to take this other interpretation of the x partial, one of a few other interpretations, I suppose. It's how fast whatever this thing is that you're taking the x partial of, how fast is that changing as you move in the x direction. And so that's why I drew all of these different y tangent lines to my invisible surface, is because I need to consider how do these slopes change as I move in the x direction. Right? So I'm representing the y partial as slopes. I'm representing the x partial as how fast are those slopes changing. Yeah. So now let's just think it through here. And again, I just, geometric appeal. I feel like this line here has a slope of about -2-ish, something. Let's say -2. This one's about, I'm going to say like -1. And this one's about -0.5. This one's about 0. This is about like +0.5. Notice those are increasing. My y slopes, as I move in the x direction, my y slopes are increasing. And so I say, in this situation, the x partial of the y partial per that picture must be positive, because those y slopes are increasing as you move in the x direction. Does everybody see that? It's geometrically very tricky, very challenging to sort of think through the geometry. This is a lovely exercise, though, because it forces you to three-dimensionally visualize what y partials look like and make a different interpretation of what x partials look like, and see that all in this weird geometric picture and make the interpretation. Yeah.
So if we want to do this with any given formula, then we would plot out the change in f over change in y, and then draw our tangent lines at each point, and then.
I mean, if all you have to work with is a picture of your surface, then I mean, yeah, honestly, I probably wouldn't like literally draw the tangent lines, but I would just try to visualize. Okay, what do those tangent lines look like, and how are they changing as I kind of come out of the board? Right, and said differently, what if you're given information about this mixed partial? If you're given information about that, then maybe what you're interested in is what does that mean geometrically? And in this case, a positive mixed second partial means that there's kind of a twist. Right? You can almost kind of see I'm putting a twist into the surface. Does that make sense?
Yeah.
Yeah. Yes.
Is that like curving towards the x?
One more time. I'm sorry.
Is that like in the circle? Is that kind of like curving towards?
What I'm trying to represent is that in the back the slopes are negative, and that as I come out away from the board, they're becoming more positive. So it's kind of like what I'm doing with my arm here. So it's weird. But again, kind of a twisting. I think twisting is the best picture for it. Yeah.
So they become positive towards the x direction?
One more time.
Are they becoming positive in the x direction?
As I go in the x direction, these slopes are becoming more positive.
So these are the slopes for
These are the slopes in the y direction, and I'm keeping track of how they're changing as I move in the x direction.
So they become positive.
They're becoming more positive. That's right. Yeah. So tricky. Anyway, that's notice there is no single variable version of this, right? So brand new ideas and geometrically challenging. Yeah.
When you say that it's greater than 0, do you mean like the z is greater than 0?
No. I mean that as I move in the x direction, the rate of change of these y slopes is positive. In other words, said differently, the y slopes are increasing as I move in the x direction. Okay. Yeah, last question. Yes.
What happens if they get more negative and then get positive?
Oh, well, we have to, there's a limit to our artistic abilities and our abilities to interpret from geometry. What we're interested in when we say a derivative is what's happening at a particular single point. Right? And at that particular single point, presumably, there's a consistent story of what's happening. Yeah. Okay. So let's move along. We're going to do 3.1 now. 3.1 is going to be about parametric curves and calculus of parametric curves. Let me point out, by the way, this is category number 4 of how to think about calculus. We've talked about how to interpret, and we're not done yet, right? But we've opened up previously 3 different contexts in which to think about various different kinds of derivatives. Graphs, what do they look like on graphs? What do they look like if you're looking at level sets? What do they look like on what I like to call the literal picture? Now, number 4, what does a derivative of a parametric curve look like? And again, separate bins, separate boxes in your mind, because all those geometric interpretations have to be different because you're looking at different pictures. Okay, so parametric curves. Y'all remember parametric curves? Position is a function of a single parameter that I like to think of as time. So by the way, again, reminder, if position is a function of time, that kind of represents a moving particle. Right? If you think about it, as a particle moves around, at any given moment in time, it has a position. And as time passes, that position changes depending on that time. Okay, so you can think of this as movement in space, movement in Rn. So how would I write down the derivative matrix? Well, here's the thing. There's only one input variable. That means there's only one column. Okay, so remember, derivative matrices, within a derivative matrix, columns correspond to input variables. Also, because there is only one variable, if you think about it, if we talk about partial derivative with respect to, well, there's only one variable. So there's really only one kind of derivative. And if you call it a partial derivative, okay, well, yeah, but there are no other variables to hold constant. It's literally straight up Calc 1 single variable derivatives. So that's why these are D's, not partial. So this is not a typo. These are actual D's. They're regular old Calc 1 derivatives. Okay, now with that noted, let me remind you all, we have an existing idea for how to take a derivative of a single variable function. Here's how you take a derivative of a single variable function. By the way, notice, indeed, we have a single variable function. Vector valued, yes, fair, right? But there's only one input variable. And this ye old formula for derivatives from Calc 1 works just fine. There's nothing wrong with this, right? And question comes up, how does this compare with the derivative matrix that we were talking about? Well, it actually compares really nicely. I claim that if you look at this derivative, you compute it one coordinate at a time. Keep in mind, right, we have these various different coordinate functions for our parametric curve. I claim it's done one coordinate at a time. And you can even see why that is, because look at this formula. Everything in this formula is done one coordinate at a time. How do I subtract two vectors? One coordinate at a time. How do I divide by a scalar? You distribute to one coordinate at a time. How do I take a limit? Okay, there's some formalities there that we're not going to worry about. I'm going to ask you to take my word for it. Turns out you take limits one coordinate at a time. I think that's pretty believable. Okay, so in fact, then, what we have is a way of making geometric interpretations of our derivative matrix. You know what this derivative matrix ends up being. And here's the way we think about it. Or keep in mind, we're talking about a parametric curve. There's my parametric curve. I'm looking at a couple points on that parametric curve. Here's my position at a time t. Here's my position h seconds later, just a little ways down the road on that curve. Let's see here. Here's how I subtract those. Keep in mind the way you subtract is by tail to head. So that numerator is just that red vector. Let me get rid of distractions now. Okay, how do I divide by a scalar? Okay, well, it's a scalar. You multiply or divide by a scalar. You're just going to change the magnitude, but the direction stays the same. So this fraction is just another vector pointing in that same direction. And now let's think about what happens when we take a limit. So there's a couple things that happen when we take a limit. We'll worry about the magnitude in a minute, but let's think about the direction. The direction that this vector points, well, it points in the direction of what I believe y'all probably recall was called a secant line. Right? So it's in that direction. And then the limit, as h approaches 0, well, this point getting closer and closer to the original point, those secant lines are going to get closer and closer. The picture's hard to draw. Closer and closer to tangent line. So the direction that this derivative vector will point in the limit is whatever direction the curve's pointing. Whatever the direction of motion is, keeping in mind this is a point that's moving along the curve. So whatever direction at that instant, whatever direction that point is moving, that's the direction the derivative's going to point. Everybody buy that? Okay. Now let's talk about the magnitude. The magnitude, let's see here, we need to take our derivative here. We want to take the magnitude. Okay, well, I'm going to take the magnitude of the numerator divided by the absolute value of the denominator. The magnitude of the numerator is distance. The denominator here, h, that's the amount of time between this moment and that moment. This is elapsed time. So the magnitude of our derivative vector is distance per unit time. That's speed. Old physics concept, right? Distance per unit time is speed. So this is a really nice conclusion. Now we've got a lot of little details running around here, but the punchline is this vector represented by the, okay, you can call it the derivative matrix, you can call it the single variable derivative, whatever, same thing. It's the vector that points in the direction you're going and whose magnitude is the speed. That's literally the definition of velocity. And I've been exerting a lot of self-control over the past week or so, trying not to say velocity when I write the derivative. But now that we've established that the derivative parametric curve is the velocity, now I can say velocity when I write derivative. Does that make sense to everybody? Nice little conclusion. Okay. All right, so likewise, and I hope you all remember, by the way, you don't need to have had a physics class to take Math219, but most of y'all probably have, maybe a high school physics class. Anyway, equivalently familiar idea that acceleration is the derivative of velocity, and so if you kind of plug those two together, acceleration is the second derivative of position. All right, so here's an example. By the way, I think y'all have probably, let me come back up here. Y'all have probably seen this and this previously, except single variable versions of them, right? Y'all have all seen the example in Calc 1 class where you have a car driving along the road and you're given its velocity as a function of time and you want to compute the distance that it's traveled, stuff like that. Right? So that's all, in fact, they don't say the term, but what they gave you by x is a parametric curve. It's just that it's a curve. It's not a curve in space, and it's not a curve in a plane. It's a curve on a line, which is a silly curve, right? It's not much of a curve. Why would they call that a curve? Nevertheless, mathematically, it is a parametric curve in R1. So all of these results here are hopefully familiar. They are morally equivalent to what you saw in Calc 1. Okay, so likewise this example, morally equivalent to what you saw in Calc 1. So let me do this quickly. Here in this example, we're given the velocity, and we're given an initial location at time equals 0. And our questions that were asked, what's the acceleration? What's the position? As functions of time. Okay, well, so we're just going to use what's on the previous page. On the previous page, we've established that acceleration is the derivative of the velocity. That's right. That's right. So there you go. And as we've already established, you take derivatives one component at a time. Hope y'all are good at all your Calc 1 stuff. Again, that is assumed in this course. It's in the prerequisite trail of this course. Make sure you're good with polynomials and trig functions and logs and exponentials and products and chain rule and quotient rule and all the old formulas for derivatives. You've got to be solid on all that. Okay, now what is position? Okay, well, wait a second. Let's think this through. Velocity is the derivative of position. So position is the antiderivative of velocity. So here we go. Position is an antiderivative of velocity. And again, one coordinate at a time, right? So I can compute, these coordinates, again, just one coordinate at a time, no problem. Again, with the single variable calculus assumption, right? So that's in the prerequisite trail of this course. Make sure you're good with antiderivatives. So standard functions, polynomials, trig functions, et cetera, substitutions, integration by parts, all the standard stuff. Okay. All right, now do keep in mind when you're computing antiderivatives, don't forget about the plus c. Easy to forget the plus c. Excuse me. A couple things I want to say about that. The plus c, a lot of students, a surprisingly large number of students, mistakenly think, I blame high schools, mistakenly think that the plus c is always the initial value, and that is absolute nonsense. It's just not true. This is not true. 100% not true. Shouldn't be true. Doesn't make it. There's no reason why it should be true. It's just wrong. It's really, really wrong. So please don't make that mistake. It is. We're going to see an example momentarily where it is straight up 100% not true. Now, why do students have this false impression? By the way, I suffered from this confusion at some point. Let's not talk about how many years ago. Well, it's because a lot of high schools restrict their examples to the very narrow category of world's simplest functions, namely polynomials. And it turns out that if your velocity is made up entirely out of polynomials, and if your initial value is at t equals 0, then yeah, it turns out sort of coincidentally that happens to work. You do get that as the result. But again, narrow category. And again, the answer doesn't matter. The reasoning is what matters. Y'all heard me say that a million times. You're going to get sick and tired of it over the next, we got 10 weeks left? You're going to hear me saying that a lot, right? As reasoning, even if the answer did work out that way, the reasoning doesn't make any sense. So it doesn't even matter if it comes up with the right answer. It's the wrong reasoning. Okay, so let me show you the right reasoning. The right reasoning is just a matter of remembering that this formula here works for all values of t. Therefore, it works for this value of t where you know what x is. Yeah. So I'm going to take this value of t, whatever the value of t is that we were given, in this case 0 as it turns out, and I'm going to plug this into that equation that I have. It's true for all values of t, therefore it's true for this value of t. And when you do that, notice that x becomes 5, 6, and a little bit of arithmetic shows that this first term becomes 3, 1, plug and chug. Right? So our big purple equation becomes this, and that's super easy to solve for c, and c is, in this case, 2, 5. So that's the way to do this. Is everybody comfortable with this process? It's no big deal, right? It's just you gotta actually show a little bit of work, and that work has to make sense. Right? Okay, and then notice, as I've already emphatically pointed out, these are not the same. Okay, so everybody's good. All right. Okay, I've already done a certain amount of complaining about this point, right? So this is, C is the same as X naught, only in this very special of special cases. It's not true in general. It's poor reasoning, enough of that. I also like to point out there's a common misunderstanding as to what this is. A lot of people refer to that as an integral, and in fact, I wasn't brought up right. I was brought up referring to that as an integral also. And then I eventually realized, it took me a while, but I eventually realized, very importantly, that's not an integral. It looks a lot like an integral. But an integral is defined with Riemann sums. An integral is defined on an interval that has bounds that you then allows you to evaluate, and the answer is a number. Not this. This is a function. Right? So we need a different word for this. This is an antiderivative. I think it's quite unfortunate that we use such similar notation for antiderivatives as we do for integrals, because they are very importantly different things. Now, yes, there is a beautiful theorem that shows this tremendously strong relationship between antiderivatives and integrals. Yeah, absolutely. Fundamental theorem of calculus. Big fan, right? Absolutely. But all the more reason to distinguish these two things. You can't celebrate how wonderful it is that two things relate to each other if you don't distinguish between those two things in the first place. Right? Integral relates to antiderivative is a shocking statement. Integral relates to integral is not even like, well, okay, I don't even know what's being said. Right? So anyway, this is one of my little personal, okay, maybe it's a personal pet peeve or something, right? But I think this is a mathematically significant point. There is a lot of mathematical insight that you will not be able to see if you don't make this distinction between antiderivatives and integrals. So please take that seriously. By the way, if you want to hear more about this for whatever reason, if you have questions, if you're not clear about the difference between integrals and antiderivatives, office hours, come talk to me. Happy to do it, right? I'll go on at great length. But do make sure that you understand that distinction. Yeah.
When writing down our thought processes on exams, are we allowed to use the verb integrate, or do we have to?
Oh yeah. Look, no. I recognize that I'm the weirdo. I'm the uptight. Yes, it's fine. Right? Again, I wasn't brought up right either, right? So I myself will refer to this as an integral, or I will refer to this as integrating. I've accepted the unfortunate reality that I have to call this the integration constant, even though it should be called the anti-differentiation constant, right? No, that's cool. I get it. I'm not gonna count off on it. I'm just saying, despite the fact that we're forced by this huge momentum of culture to blur this distinction in many cases, is something you should fight against. That's really my main point. Yeah. Yep. Okay, real quick. It says so on the content syllabus, but all the Kepler stuff at the end of section 3.1, you are absolved. Right? It's not part of the course. It's very cool. It's very historical. Yeah, neato. Right, but it's not what we're doing in this course. It's a kind of it's a digression that we just don't have time for. That said, you are responsible for this, what they call proposition 1.4 that you'll find in that section, or that part of all that Kepler stuff. So this one thing is actually quite useful, and it is something that you need to know. So no big surprise. Basically, this is just saying that when you have vector-valued functions, dot product and cross product have corresponding product rules. I don't think it's that surprising. It's also not hard to prove. If you want to prove either one of these, all you got to do is write each of these vector-valued functions in terms of their coordinates. Just break everything down into coordinates. x1, x2, x3, y1, y2, y3. And then you just crank out the dot product, take the derivative, use your old single variable calculus rules, in particular the single variable product rule, and reassemble, and you'll find you get exactly this. It's not deep water, but it is something you need to know. Okay. Chain rule. Okay. Y'all remember the chain rule? I assume that y'all are strong with the single variable chain rule. My purpose on this page of the notes is not to teach y'all the single variable chain rule. I know you know the single variable chain rule. My purpose with this page of notes, this whole page of notes, is about the single variable chain rule. The reason I do this is because I'm setting up an analogy. There is a particular narrow take, just a particular perspective. If you take this one particular perspective on the single variable chain rule, then I can say, check it out, the multivariable version is exactly the same. Right? So this is a perspective that makes extending to the multivariable context super convenient. So don't think of this as, you shouldn't be looking at this page of notes thinking, do I know this or do I not know this? Think of it as I'm guiding you towards a particular perspective. Okay, so here we go. I want to talk about derivatives. Y'all recall that derivatives can be thought of in different ways, and here's the one I want to use here. Again, narrow, very particular, setting up an analogy. I want to think of derivatives as something you multiply by input velocities to get output velocities. And you've heard me say that before, right? And I hope this is a familiar point of view from single variable calculus. But if x is moving on the x-axis, and if that's the input to some function f, well, then the output will be moving on the y-axis. There will be an input velocity, and there will be a corresponding output velocity, again related by the derivative of that function. So this is the point of view I want to take on derivatives. Forget slopes, right? Forget whatever other points of view you might have had. So it's a relationship between input velocity and output velocity. Is everybody happy? Everybody remember this previously discussed? Okay. So yeah, here's a picture of what happens when you compose functions. And so look, I've got a single variable function here where x goes in and y comes out. Single variable function. By the way, I can relate input velocity to output velocity by way of the derivative of that function, which I'm going to call dy dx. Right? That's how we interpret derivatives. Oh, let me do that. Okay. Let's see here. Now next, let's see here. I can relate, color choices. I can relate this part of the diagram. This is just another function. Here I've got a second function called g. Y is the input, z is the output. And as y moves, that is the input velocity for this function g, and that will have some resulting output velocity, which again relates by way of the derivative. And in this case, the derivative of g, which I'm going to call dz dy. Right? Same basic, different variables, but same basic idea. Okay. All right, and now there's a third function in this picture. The third function is the composition. After all, what comes out of f is what goes in to g. And so the composition, I can think of the composition as a function. X is the input, z is the output, and let's see here, that input velocity x prime gives rise to a output velocity z prime. The composition is the function that does that, and so its derivative, dz dx, is what turns x prime into z prime. So all I've done so far is I've just applied this interpretation 3 times. Okay. All right. Now, what are we going to do with this? There's different. There's different ways that you can sort of proceed from here. You can, and I've done the algebra. I've got it for you down here. If you really want to see how the algebra, how you take these and you plug this one into there and the blah blah blah, you can do that if you'd like. And just for the very broad strokes of it all. The big idea is you take this formula for y prime and you stick it in here. That makes this formula for z prime turn into this. And then, of course, you can also look at the composition. The composition is another formula for z prime. So I have 2 formulas here for z prime. And if you have 2 formulas for z prime, then the thing there and the thing there have to be the same, and there's your single variable chain rule. So you can think of that as, the algebraic consequence. But there's something about that I find that very clunky, right, to be fair. Let me show you what I think is the much easier way to think about it. And that is, what we're doing is we're starting off with an input velocity and we're trying to determine an output velocity. And let's think of this as just a succession of multiplicative factors. After all, that's what all these equations say. These equations say that one velocity relates to the next velocity by way of a factor. So if you multiply by a factor here, and then having done that, you multiply by a second factor, altogether, what's the whole factor? Well, the factors multiply. Right? Silly example. If I give you a number and I tell you to multiply it by 2, and then I tell you to multiply that result by 3, altogether, you've multiplied by 2 times 3. Factors multiply. Right? So that's really what's going on here. On the one hand, I've got a factor followed by another factor. Altogether, that whole factor is the product of the individual factors. That's really, I think, the cut through the notation and the algebra. Morally, that's what's going on. And I'm out of time, so I'm going to have to draw the line right here. We're going to pick up with this next time. See y'all later. Have a good rest of your day. Don't forget to talk to me about attendance if you didn't get marked down yet.